In this video, we will introduce the concept of sequences and series and also the sigma notation. The terms sequence and series are often used interchangeably. However, we should note that there is a distinct difference to these two terms. A sequence is an ordered list of numbers, and the terms within a sequence are usually separated by commas. For example, we have the sequence of odd numbers 1, 3, 5, 7, and the sequence of the powers of 2, 2, 4, 8, 16. As long as there is a pattern that exists within the list of numbers, it is considered a sequence. Usually, the numbers in a sequence are represented by either U subscript n or T subscript n, where n refers to the nth term of the sequence. So for example, in this sequence of odd numbers, we will have U1 equals to 1, U2 equals to 3, U3 equals to 5, U4 equals to 7, and so on. And we can show that eventually Un will be equals to 2n minus 1. And thus, we can express the nth term of any sequence as a function of n. In example 1, we are asked to find the first 5 terms of the sequence Un equals to 3n squared, where n is all positive integers. And thereafter, we will have to find the sum of these 5 terms. So U1 will be equals to 3 times 1 square, which is 3. U2 will be equals to 3 times 2 square, which is 12. U3 will be 3 times 3 square, which gives us 27. U4, 3 times 4 square, which gives us 48. And finally, U5 will be equals to 3 times 5 square, which gives us 75. And to find out the sum of the first 5 terms, we simply have to add them up. So sum of first 5 terms will be equals to 3 plus 12 plus 27 plus 48 plus 75, which gives us 155. So we can see that if we want to find the sum of any number of terms, we can simply just add them up. But it will be very tedious if we have a lot of terms to add up. And hence, we have the second part of this video, which is on series, and there will be some standard formula to help us evaluate the sum of several terms in a series. In contrast with a sequence, a series is the sum of the terms of a sequence. Meaning to say, for 2 of the sequences that we have given earlier, the corresponding series becomes 1 plus 3 plus 5 plus 7 and so on. And the second sequence becomes 2 plus 4 plus 8 plus 16 and so on. Usually, series are represented by capital S subscript n, and this means the sum of the first n terms of the series. So Sn is equals to U1 plus U2 and U3 and so on all the way until Un. Instead of writing out the entire string of terms to be added in a series, the sigma notation can be used to simplify expressions of a series and thus used to represent sum of a series. So for a series with sum of U1 all the way to Un, we can replace it with a sigma notation like this. How we interpret this is sigma represents the summation of the term UR, where R can be changed. And how R will be changed is from R equals to 1 and proceeds on all the way until the last term N. So this is essentially the same as summarizing this. So we can see that when R is equals to 1, I'm going to substitute 1 into this expression to get U1. When R is 2, I'm going to substitute 2 inside here to get U2. When R is 3, I'll substitute here U3. and so on. Eventually, the last term I substitute will be when r is n, which gives me un. And the summation, the sigma notation tells me that I need to sum up all of these terms together, and hence they are equivalent. Using this notation, there is also more flexibility in defining series that start at n at other values. For example, we can have u3 plus u4 and so on until u20. It will be written as 20 summation r equals to 3 of ur. So we are going to sum all ur terms from r equals to 3 to r equals to 20. And also, if we have the sum 1 plus 2 plus 3 all the way until 50, we can write it as a summation up to 50 from r equals to 1 of the term r, such that when we substitute r equals to 1 in, we get 1. When we substitute r equals to 2 in, we get 2, and so on, until 50. In example 2a, we need to convert this series of sum of odd numbers into sigma notation. So we can say that this is equals to summation of 2r minus 1. 2r minus 1 or 2r plus 1 are both general expressions for odd numbers. Now that I have chosen 2r minus 1, I will need to start from r equals to 1, because when I substitute r equals to 1 into this expression, I do get a 1, which is the correct starting point. And for the ending point, it will have to be 51, because when I substitute 51 into this expression, I do get 101. Also, we can also have the flexibility to write it as summation of 2r plus 1, but we will have to change the limits correspondingly. So if the expression is 2r plus 1, the value of r has to start from 0 instead of 1, and it has to end at 50 instead of 51 to give us the same starting and ending values of 1 and 101. For example 2b, we now have to convert this series into sigma notation form. And we note that every term is in fact a square term. So 4 becomes 2 square, 9 is 3 square, we have 4 square and 5 square and so on, all the way until n square. And therefore, this is the same as writing a summation of r square from r equals to 2 to n. In using the sigma notation, there are some formula that we can also employ. The first is the summation of a, which is a constant. It gives us a times n. How this is obtained is pretty simple. Since a is a constant, the summation of a will be simply a plus a plus a for n number of times. And therefore, this becomes n times of a, which is an. Next, we have the summation of r from 1 to n. This is essentially summing up all consecutive numbers from 1 to 2 to 3 all the way to n. And this is an arithmetic progression which we will be going through in a separate video. For now, we just have to recognize that this form is an arithmetic progression and the formula can be derived to be n over 2 n plus 1. Next, we have the sum of a geometric series where each term is a constant multiple of the previous term. So we have summation of a to the power of r, which is the same as a to the power of 1 plus a to the power of 2, a to the power of 3, and so on until a to the power of n, which is a geometric series because from one term to the other, we always multiply by a constant a. And because it is a geometric series, we will be covering it in a separate video as well. And for now, we just need to recognize that this form gives us a GP, and the formula will be a to the power of n minus 1 over a minus 1. The following two formula are summation of r squared and r cubed, and the formula will be given to you in the exam if required. Thus, there is no need to memorize them. Some properties of the sigma notation that we have to know are, firstly, we can split up the addition or subtraction of terms into separate summations and at the same time bring out constants from the summation. This formula is useful when the term to be summed contains two or three types of terms that require different formula to evaluate. For example, we might have the sum of 3r squared plus 2r, which there is no formula for us to evaluate. But if we can split them up into 3 summation of r squared plus 2 summation of r, there will be formula for us to evaluate each of these two terms separately, and thus we have evaluated the entire summation by breaking it up into smaller terms. Next, the r value of the summation doesn't have to start from 1, and thus the number of terms to be summed sometimes becomes not so obvious. However, we can calculate the number of terms in a summation which starts from r equals to m and ends at r equals to n using the formula n minus m plus 1. Also, we have this formula which is very useful when evaluating summations that do not start from 1, when we only have the formula for summations starting from r equals to 1. So for example, if we are required to do the summation of r equals to tan of r squared, there is no formula for us because for summation of r squared, the standard formula that we know of starts from r equals to 1. Hence, I can change this into summation of r equals to 1 of r squared minus summation of r equals to 1 to 9, which is one term before our actual starting point of r squared. And thus, we can apply the standard formula to evaluate both of these to give us the required summation. Finally, we can also have the starting term of the summation changed by 1 or 2. We can either start the summation at the preceding term by changing r into r plus 1, or we can start the summation at the succeeding term by changing r into r minus 1. How this works is we can simply change all the r into r plus 1 or r minus 1. And I will make use of r plus 1 example. So for n summation of r equals to m of ur, I am going to change all the r into r plus 1, which gives me summation of u r plus 1. And at the starting point, I am also going to change the r into r plus 1. And if I simplify all of them, it becomes summation of u r plus 1. I can bring this one across, and therefore I get r equals to m minus 1 and n minus 1 at the top. In example 3, we are now asked to evaluate the sum of these numbers over here, which are actually the squares of odd numbers. So first, let's rewrite it in sigma notation form. 81 plus 121 and so on until 625. I can write it as summation of 2r minus 1 from r equals to 5 to 13. But if I write it down in this term, it will be very difficult for me to evaluate because the base does not start from a 1. So instead of writing it in this form, I can also choose to write it in summation of 2r plus 7 square from r equals to 1 to 9. You can do a conversion, they will be equivalent to one another. Now based on this, we have summation of r equals to 1 to 9 of 4r squared plus 28r plus 49 which we can split into the three terms. 4 summation of r equals to 1 to 9 of r squared plus 28 summation of r equals to 1 to 9 of r, and finally summation from r equals to 1 to 9 of 49. Each of these three summations, we have a formula for them. So we can evaluate this sum pretty easily. The first term becomes 4 multiplied by 9 over 6, 9 plus 1, 18 plus 1, because we have the formula summation of r squared from r equals to 1 to n equals to n over 6, n plus 1, 2n plus 1. And this second term over here is 28, 9 over 2, 9 plus 1, because we have the formula for summation of r equals to 1 to n of r being n over 2, n plus 1. And finally, we have 49 times 9, because summation of r equals to 1 to n of a constant term is simply a times n. And therefore, we can press our calculator to evaluate this sum, which gives us 2841.